The topic today is section 10.5, area and arc length in polar coordinates. The objectives that are stated there means that we're going to be taking the polar information we talked about in the last section and applying calculus to it. So we'll be finding the area of a region bounded by a polar graph, find the points of intersection of two polar graphs, find the arc length of a polar graph, and find the area of the surface of revolution in polar form. In order to understand how you get area, recall that when we worked in our rectangular system, when we wanted to first find area way back in Calculus 1 under a function, we had that idea of having a function and making some representative figure, such as a rectangle or a trapezoid or part of a parabola or whatever, to represent that and break it into small pieces that, when added together with a sigma, with a summation, you would get an idea of how to find the area approximately. And then once you had that down, if you did that sum for infinitely many rectangles, we knew that we would get the exact area. So it's a continuation of the theme that we've started doing a couple of times. So we're just going to continue it here. So knowing the area formula for a rectangle or a trapezoid or whatever it was important because we had to break it down to that simple figure for which we did have a simple expression for estimating what we're trying to find. So I want you to think about a circle, and if you have two radii for that circle, the part that you've created there, the sort of the piece of the pie there, is called a sector. And to find the area of that sector, there are two pieces of information you'll need: the radius and the angle of that sector. And so, for a circular sector like that, it ends up that the area of that sector is 1/2 r squared theta. 1/2 r squared theta. And so, given this simple expression for the area of a sector of a circle, we will then apply that to a polar curve. So if I had some polar curve that looked like this, maybe. Oops, let me make the y-axis a little bit bigger. If that's my curve, then what we'd want to do is realize that we're going between an angle here. Let's say this is at theta equals alpha to theta equals beta, kind of like the A and the B that you see above in the rectangular. And so we're trying to find the area of that region that's right here. Of course, that's not a circular thing, so we can't use the area of a sector formula directly. But what we can do, let me draw a little bit bigger picture of that. What we can do is, if this is our curve, and I'm not going to draw the alpha and beta, but if I draw in a representative sector, kind of like drawing in a representative rectangle, and we'll have to treat one of those two as the radius of the circle. It could be the larger or the smaller, kind of like the left-hand or right-hand rectangle. So one of those will be the R that we're using. Let's say it's this one on top because it's joined to the curve at that point. The other part of that arc, the end of that radius, isn't connected to the curve right there. And the change in the angle that we'll experience we'll call delta theta, kind of like delta x. And so if we add up from the first sector to the nth one, the area of 1/2 of r squared d theta, oops, I forgot to write in something. Let me back up just a second. That r is correct, but I'm going to think of that kind of like, instead of using x, we use f of x. I should have done that here as well. So that's going to be some f of theta sub I squared d theta, or delta theta, excuse me. I'm getting ahead of myself. Delta theta. And then if we take the limit of that sum as n goes to infinity, we'll get the exact area of that region within that polar curve between alpha and beta. So as we've seen before, with a limit of a Riemann sum, that area becomes an integral from alpha to beta, kind of like going from A to B, of 1/2 of f of theta squared. And I usually write, the reason I paused there for a second was I usually write r here, but I'm trying to kind of underscore the fact that r is a function of theta squared d theta. And so that's our formula for area of a polar curve. All right, so now that we have that idea firmly in our grasp, I'm going to move on to the page where it says Theorem 10.13, area and polar coordinates. The first one is like what I wrote, except for they've pulled the 1/2 out, which I will normally do as well. But the way I usually write this is not with f of theta, but as r, because it's generally given in terms of r instead of f of theta notation. So this is, generally speaking, the better one of the two, in my mind, to memorize. All right, so let's go to our first example. Find the area of one petal of the rose curve r equals 3 cosine 3 theta. R equals 3 cosine of 3 theta. All right, so to graph this relatively quickly, they told me it's a rose curve, so I'm kind of clued in as to what's going on. Since 3 in front of theta is an odd number, that means I'll have 3 petals. And the coefficient 3 in front of cosine theta says I'll multiply my largest value of cosine, which is 1, by 3, which means that the petal will be 3 units long. That'll be the furthest we get away from the pole, is a maximum of 3. And of course, when cosine is negative, 3 times the negative number will make r negative, which will put us into the quadrant 180 degrees out. So what I really need to graph this is just, where do I start? Those 3 petals will be, by the way, evenly spaced around the whole circle. And so really all you need to know, so that means they're 120 degrees apart from each other, because 360 degrees divided by the 3 petals means that they're spaced by 120 degrees. All I really need to figure out is, well, what's happening at 0? Cosine of 3 times 0, cosine of 0 is 1. 1 times 3 is 3. So when theta is 0, r will be 3. So that means that there's going to be a petal that extends out like that. Then 120 degrees around, there'll be another one. And 120 degrees later, there'll be another one. Now this doesn't have the precision of what we talked about last section, but I'm not really going to dwell on the graphing right now. I'm just going to assume that you can do that. What I want to do is concentrate on, well, what do I need to do to find the area? So one of the things we're going to use a lot in this is symmetry. When I started at 0, I started at the end of the petal with an R value of 3, and at some point it came back to the pole. And so if you think about that, I'm going to just draw a bit of this a little bit bigger. When we started at 0, we were at 3, and the angle went until we got back to the pole. So let's say the pole's right there. Well, as we go around and get those values, it's going to be important to figure out, well, when does it actually hit the pole again? That's really important to us, because I could find the area of just this part of it and use symmetry to say, well, if I doubled that, I would get the other half of that petal, thereby getting the correct answer. So what I need to know is, when does r equal 3? And so this gets back to some pre-calculus stuff. When is 3 cosine of 3 theta equal to 0? So if I divide both sides by 3, and by the way, if you graph this using the techniques from last section, you might already know what angle it is where that was 0, and you may not have to go through this process. Okay, so when is cosine equal to 0? What 3 theta value would make cosine give you a 0 answer? Well, we know cosine is 0 at pi over 2 plus pi n. Now that gives us actually all answers, which we're not as interested in this problem, but just to cover all bases. That's when we'll have the radius equal to 0. So dividing both sides of that equation by 3, we get pi over 6, which is actually what we need. And then if we wanted to know where other places it actually gets all the way back to the pole, this is an expression for every time that happens. Of course, that may come up in some problems where you know not the first one, but the fifth time it happens or whatever. So, as I said, pi over 6 is a good one. So, the area will be 2 times, because we're using symmetry and we're doubling the red area you see above to get the entire area of the red and the kind of chartreuse greenish color. So 2 times our formula 1/2 of the integral from theta equals 0, which is where we started. This curve right here is at theta equals 0. And by the time we get back to the pole, at that point, we're at theta equals pi over 6. So our integral will go from 0 to pi over 6, which is just half of the area we're trying to find. Hence the doubling is the very first thing I wrote down 2 times. R, which is 3 cosine of 3 theta, quantity squared d theta. I just realized why my handwriting doesn't look as good as I like. It's because I was using the mouse. I don't know where my head was. Sorry about that. It was looking really nasty there for a while. I couldn't remember what I'd done before. My apologies. All right, so let me move this down a bit. Should have done that with the mouse while I had it, because it actually moves it better and faster. Oh well. By the way, another way to have done this, if you thought about it, is we could have gone without doubling and gone from, say, negative pi over 6 to pi over 6, and that would have given us the correct answer as well. All right, so 2 times 1/2 is 1, so that basically cancels out. That's gone. So we're going to integrate from 0 to pi over 6. Doing the squaring, that's 9 cosine squared 3 theta. See how much better my handwriting is now? I was wondering why I was so slow. My apologies. Wow. What a difference this makes to have the pen instead of the mouse. Okay, so how do we integrate cosine squared? Well, this is going back to the trig antiderivatives that we talked about before. After pulling the 9 out, we're going to rewrite cosine squared using the power reducing identity, and that will become 1 plus cosine of double the given angle. Doubling 3 theta gives us 6 theta over 2. So that 2 in the denominator is a constant that I can pull out. And now I'm integrating from 0 to pi over 6, 1 plus cosine theta, cosine of 6 theta, excuse me, d theta. All right, so the antiderivative of 1 is what? Hopefully you didn't get caught and say x, because this is d theta. It's theta, not x. Wasn't trying to make it a trick question, but that is a thing you need to watch for. That's theta. Plus the antiderivative of cosine of kx dx, the little formula we learned before, is 1 over k, so 1 over 6. The integral of cosine is positive sine of the given angle, 6 theta, evaluated from 0 to pi over 6. Okay, so substituting, we get pi over 6 plus 1/6 sine of 6 times pi over 6 is pi, minus 9/2 times the quantity 0 plus 1/6, oops, 1/6 sine of 6 times 0 is 0. Starting at the back end, both of those terms inside the second set of parentheses end up being 0. So minus 9/2 times 0, that back part is just something we can ignore. So see, 9 pi over 12 would reduce to 3 pi over 4. And I'm distributing the 9/2, and 9/2 times 1/6 is 9/18, which is 1/2. I'm sorry, 9/12. Ooh, I'm sorry. Woohoo, where'd that 18 come from? 9/12, which reduces to 3/4, times the sine of pi, which is 0. And so our final answer is 3 pi over 4. All right. So that's actually going to be a good place to stop and just make the next part its own section. So I'm going to stop here. Have a good one.